Hello, everybody. It's me, David Getzloff, back again with another case study presentation about Rust. And so today I'll be talking about ownership in Rust and concurrency. So in working with heap memory, we talked about a couple of different ways to do that. And so the first is with manual allocation, like with C or C++. And we talked about this being very fast, but putting additional responsibility on you as a programmer and the potential for memory leak or for dangling references. And so then the other type that we kind of talked about was automated allocation. And we talked about that using a garbage collector in languages like Python and Java and Go and a whole bunch of others. And basically, it abstracts us away for us as programmers, but it has a much slower runtime with that. And so what Rust is able to do is be fast, but then to also use automated allocation by enforcing ownership rules at compile time. So Rust's 3 ownership rules are as follows. This is pulled straight from their documentation. The first is that each value in Rust has a variable, and that's called its owner. A value can only have one owner at a time. And then finally, that when the owner goes out of scope, the variable is dropped. And so what we're going to do here for the rest of the video is kind of work or look at how that works and how it helps with concurrency. So what I'd like to do first here is just take a peek at this Rust example code. And so what we've got is 2 functions. We've got a main function, and then we've got this helper function. And so in the main function, we have S1 being assigned to a string, which is hello world. And then what we're doing is we're going to print that S1 and then pass it to helper. And so when we're passing, this is, importantly, this is not the built-in string. This is a string that you're able to append to, which means that out here, this is stored on the heap as a pointer to this memory location, and then it's kind of like a linked array, basically, of characters. And so what we're able to do is we're able to push additional parts of string on here and essentially concatenate. And so what we're going to do is we're going to pass S1 here to our helper function and add this exclamation point to the end and then print it again. And then we're going to try to print S1 again. And so here, as I run this, we can see that this is not able to compile correctly. So below, we've got this diagram of what's happening in our program. At the beginning, we've got S1, which is pointing to where hello world is on our heap. And then when we pass it to S1, that's also where S1 points. So they're both pointing to the same thing. But when our helper function goes out of scope, as we saw, it will clean up hello world and we'll end up in an instance like this where at the end where we try to print S1 for a second time, that memory's actually already been released. And so when it tries to print and release it again, because S1's just about to go out of scope, then that's where our compiler error comes from. So hopping back here to our code, this is how we're able to get around this in Rust. And so we can see that we still have our main function. We can see that we've still got a string, but this time when we're passing it a reference to the memory location where S1 is. And so then we are doing our mutation and printing it again. This actually all works. So what's going on here is that when we're running in our helper function and we're passing by reference, basically, instead of value, is S is pointing to a different memory location, which is pointing to S1. And so then the S1 is pointing up here. So then when helper goes out of scope, our pointer to S1 goes away and S1 is still referencing hello world. So we're able to print that as well as then we mutated it, we added this exclamation point, but then print it again. So the next thing that I wanted to do was just take a quick look at how threading works in Rust. And so here we've got a main function, and we've got a thread inside of it. And so we're spawning a thread, and for a loop of 10 times here in this thread, we're just going to say hi from the thread and then a number. And then sleep for a millisecond and then do that again. So we're going to do that 10 times in a row. And meanwhile, our main function is going to do the same thing, but only 5 times in a row. So let's run this and see what happens. So together, but there's kind of that interleaving from the main and the spawned, and then the spawned and then the main back and forth. Where then if we move this join statement, so comment this out, and move it up here, what we'd expect to see is for the main to wait on this thread until it's complete, parentheses here, wait on the thread and then do continue on after that. So we'll run it again really quick. And that's what we see this time. We see the thread do its loop of executions, and then the main function follow after that. So where this becomes really powerful in Rust is combining these two ideas together with the concurrency and then the ownership model. And so here, actually, what I have is a little bit of Python code that I wrote to illustrate a data race, right? And so in this, we have a global variable called global var. It's integer, which is 0. And then we've got these two helper functions, which are incrementing and decrementing that global variable. And so then down here in our main, we've got one thread who is going to add, basically in a loop, it's going to add 1 million to the global var, and this other one is going to subtract 1 million from the global var. And so what you might expect, if you haven't done that much work with concurrency before, is, or at least with Python, is that this will be 0 here at the end. So after we start and then wait on these threads, that the value of global var will be 0 at the end. But here what we actually see is that the value of our global var is pretty close to 600,000. And if I run this again, we get a different result and a different result and a different result. And I'm a little surprised none of these have been negative so far. But basically, that's just due to the non-determinism in these threads and the data race that's going on. So depending on the interleaving of these instructions, if the increment is cut off by the decrement thread, it's possible to not have this +1 get registered correctly, or vice versa, that the increment will cut off the decrement. So what I've tried to do here is kind of just rustify that code that we just saw in our Python file. And so we have this global variable here. Really, it's not really a global, but it is inside this main function. And we're printing out its value. And then we're going to start this thread and add 100 to it. I'll actually kick that up to 1 million. And so we'll be adding a million and a million both times, and printing out what the value of the global var is in each of those threads. Because what actually happens here is when we're trying to pass by reference, which is what we're doing when we're passing in and we're using just directly this global variable, what Rust will do in its ownership model is it'll actually make a copy of each of those. So if we'll see when we run this, we've got global variable from our main function. Global variable is 0 and the address is this. That actually neither of these threads mutated that original global var at all, because here we're printing it again at the end after our join, and it's still equal to 0 and the address is still the same. So here we have on the left our scope, and the global var, wherever you see it, it's actually pointing to 3 different values. So as soon as this increment thread starts up, it creates a new instance of global var. It copies it into this new address value. And then same thing when the decrement thread starts, it copies whatever's here and has a new reference to it. And so then increment thread and decrement thread are both able to work on their task, but not have to worry about corrupting the data that's there. And so what you might be thinking from before is, well, what if we just do it by pass by reference instead of pass by value? And so I'll go back here to the code and show you a second example of why that doesn't work either. So here we are back at our second threading example here. Same setup, the main and then the increment decrement thread. And then at each point here, once at the beginning of the main and once at the end, we're printing the address value and where it's actually stored, and then same here. But basically, the difference here is this global variable that's equal to 0, excuse me. And then here we're letting the address be where that global variable is stored. So we're trying to pass by reference to that address as opposed to the actual variable. And so here I'll try to run that, and we can see that it doesn't compile. And so I will bring up the error message a little bigger and explain that to you. So here is that error message that we just got. There was a couple. I had to search through and find this one because they kind of are all based off of what's happening here. But there's a couple others. And basically this says that the address value has been moved, right? And it says that here in line 5, we had that address, which is the where the global variable was being stored. And then here in 8, we moved it into this increment thread. And then in line 15, it's used again after the move. And so what exactly does that mean? Basically, it comes back to what I said earlier about Rust's ownership model and enforcing that number 2 rule. And that is that a variable can only have one owner at a time. And so what's happening is we're passing that address variable from main, and we're letting the new owner be the increment thread, kind of like this. So we'd hope to have something like this, where I said where we point to the address where global var is, and then here is where global var is at 0, but we have these 2 other pointers. But like I said, we can only have one mutable borrower at a time. And so we do this first borrow successfully here when the increment thread started up. But the second one here in red, we're unable to do because we can only have the one borrower. And so that's what prevents us then from incurring the data race where 2 threads are kind of fighting at the same time to update that variable. And we might end up with the wrong value like we saw with Python. That can't happen here. We can only have the one singular thread mutating the value at a time. That's just a little bit about how ownership and concurrency work in Rust. It's really interesting to see a language, to study a language that is kind of designed with those purposes in mind. And I hope you enjoyed this presentation.